Now we'll spend some time talking about analysis and the guiding principles that we'll use for the rest of this term. First principle is worst case analysis. For us, worst case analysis is going to be the running time bound that holds for all input of length n, or actually, to be a little more specific, holds for all input of length n above a certain value. But we make no assumptions about the types of input, and we make no assumptions about whether the input's complicated or simple. This is as opposed to average case analysis or benchmark analysis, both of which require some domain knowledge. Second guiding principle is we ignore small constant factors and constants. This is my computer scientists are lazy mathematicians principle. Why do we do this? We do it for a number of reasons. One, it's easier to do the analysis this way. If we ignore constant factors and constants, then things get a lot easier. It also allows us to ignore the machine architectures and the implementations and focus on the algorithms themselves. Because lots of times those constants and constant factors are very tightly integrated into the architecture and the implementation. And it turns out we lose very little predictive power by doing this. We can do a very good job of analyzing the algorithm's performance by ignoring the constant factors and the constants. And then the third guiding principle is asymptotic analysis. We focus on running algorithms for large values of n. We look for the bounds, upper and lower, that give us reasonable estimates on performance using asymptotic analysis. So for example, 11n log to the base 2 of n plus 11n is better than 1/2 n squared. Also, we'll need to talk about, for which values of n it is better. And it turns out, as far as we're concerned, only big problems are interesting. If you want to sort an array that's only 100 or even 1,000 elements long, just use insertion sort. It'll work just fine, despite the fact that it's an n squared algorithm. You don't need to go to the effort of trying to optimize a problem like that. So finally, what's a fast algorithm? Well, sort of the working definition of a fast algorithm is that it's a worst case running time grows only slowly with respect to the input size. So the holy grail of a fast algorithm is linear or even sublinear time algorithms. You can actually think of a sublinear time algorithm if you sit there and think for a couple of seconds. More on this later. Now we'll move on to asymptotic analysis.